In this problem, we're going to focus on finding the inflection points of a function. And here we have our function x cubed minus 9x squared plus 24x minus 10. Now, inflection points are places where the second derivative, in this case f double prime of x, changes sign. So we're looking for places where f double prime changes sign. That would mean that the graph of our function changes from being concave up to being concave down, or vice versa. So that means we got to start by finding our second derivative. So first of all, f prime of x, our first derivative, should be 3x squared minus 18x plus 24. There's our first derivative. But we want to talk about inflection points. That means we need the second derivative. So we want f double prime of x. Here in this problem, we take the derivative one more time. We should end up with 6x minus 18. So there is our second derivative. And just like I did in the previous examples, I'm thinking about places where f double prime could change sign. It could change sign when it's 0, and it can change sign when it does not exist. So we'll start by taking 6x minus 18, setting it equal to 0, and we'll solve for x here. So 6x equals 18 gives me x equals 3. Now I can't automatically assume that this is going to be an inflection point because I need to make sure that that second derivative changes sign. So we'll hold on to that point for right now, because I also need to think about places where f double prime does not exist. However, in this case, the second derivative is a polynomial, so that means that we don't need to worry about that. F double prime is a polynomial, so that means that it exists everywhere. It means we don't have any additional partition numbers here. So my next step would be to construct my number line for my second derivative. So here we'll say here's f double prime. We only had one partition number. We had x equals 3. And again, just to kind of build some good habits here, at x equals 3, we said that the second derivative was equal to 0. So I'm going to put a little 0 above 3 for my second derivative. And then at this point, we'll take numbers on either side of x equals 3 and plug those into our second derivative. So on the left-hand side of 3, how about x equals 0? I think that would be easiest to work with. So f double prime of 0 would be 6 times 0 minus 18. 0 minus 18 gives me negative 18. So that means that f double prime is negative on the left-hand side of x equals 3, which tells me that the graph of my function must be concave down there. Then I'll take a number on the right-hand side of 3. How about x equals 4? F double prime of 4 would be 6 times 4 minus 18. Here I've got 24 minus 18. This time around I get a positive 6. So the sign of f double prime is positive, which tells me that my function must be concave up on that interval. So as soon as we see a sign change in our second derivative, that means that we have a sign change in our concavity, which means that x equals 3 is an inflection point. So we've verified that, yes, we have an inflection point at x equals 3. The last thing that we need to do to finish this up then is we need to find the y value corresponding to that. And just like we did in the last section, for the y value, we're looking at the original function. We're looking at the graph of, the equation of f of x. So for our y value, let me just copy that down here. F of x equals x cubed, and I already forgot the rest. Let me scroll back up. Minus 9x squared plus 24x minus 10. Let me just make sure real quick. Plus 24x minus 10. Yes, okay. So if I want to find the y value corresponding to x equals 3, I'll plug 3 into this function, so that would be 3 to the third minus 9 times 3 squared plus 24 times 3 minus 10. So I'm going to crunch some numbers here on my ends just so that I don't make a silly mistake. And I ended up with a y value of 8. So that means that I have an inflection point at 3, 8. And what we'll see in our graph is we'll see a change in concavity. It's going to change from being concave downward to being concave upward. Showing that in a graph is a little bit trickier than, say, a minimum or a maximum value, but we'll get some practice with sketching curves later on in this section.